Welcome back, my friends, to another episode of Uncertainty and Probability Theory, the Logic of Science. This is William M. Briggs. We are on episode 50, plus a couple of others. So I guess this is really our anniversary. We've been at I did 2 other weeks, which I didn't name, and I've just thrown my chalk onto the floor again. So we've done this for a year now, and we're just moving into models. We're trying to understand exactly what models are, what uncertainty relation to empirically measured things are, and all that kind of thing, because we're going to be concentrating on science. But probability is not restricted to science. It's not restricted to measurable things, measurable in the real world, that is. Just as logic isn't. We can have logical relations of any propositions that we care to name, and we can investigate the logical connections between them. So can we with probability. And one of the concepts, we talked about it last week in some depth, but there were some questions and some confusions and so forth. So we're going to have to talk about this idea of independence, which is the classical word. This is the word that is used in every probability and statistics book that I know, versus, except for a couple of exceptions, and irrelevance, which is the word that I favor. And I think irrelevance is a logical word, and so probability is the completion of logic, so we should stick to that for that reason alone. And because of the connotations that independence has with 2 errors, which we're going to emphasize again today. And so I'm going to quote from, and I don't know where my copy is. Naturally, I had it earlier and I can't find it. I'm going to quote from Ross, a very well-known book. It's gone into, I don't know how many editions now. Sheldon Ross, Introduction to Probability. It's a very good book. I recommend the book highly. I think people should get a copy of it. Doesn't matter which version that you get. Get an earlier one, I guess, because it's less textbooky looking and less, bloated as all sorts of modern books are nowadays for used in colleges and so forth. But he has this. I want to read this. I'm going to have a quote on this on the web page, and wmbriggs.com or wmbriggs.substack.com on the class notes. And so you'll read this more completely. But he makes a number of important mistakes in this short paragraph. And he makes them very clearly, which is to our benefit, so we can look at them. I've only written a sketch of it up here, so I'm going to read you this quotation from his book. It's on page 87 of the edition I have, which I can't remember where I stuck the thing. I had it up ready to go, and then I was looking at it, and then set it down, and it's disappeared. Anyway, we have things like probability of E and F, which are just propositions. The previous example of his chapter, he says, show that the probability of E given F, the conditional probability of E given F, is not generally equal to the probability of E, the unconditional probability of E. Alarm bells should already be ringing for us. In other words, knowing that F has occurred generally changes the chances of E's occurrence. Generally changes the chances of E's occurrence. In the special case where probability of E given F does in fact equal probability of E, we say that E is independent of F. That is, E is independent of F if knowledge that F occurred does not change the probability that E occurs. And he gives Bayes' theorem there after that. Well, that's not right. There is no such thing as the probability of E. The probability of E doesn't exist. The probability of E can be any proposition you like. Unconditional probability does not exist. You cannot think of a probability, you cannot think of any probability for any proposition A that does not have some conditions. You must have some conditions. At the very least, you have the implicit or tacit premises about the definition of what A is. What does it mean? If anything, it may not mean anything. It may be gibberish. But that still forms part of the basis with which you use to judge the uncertainty of A. You cannot write down, and I invite all skeptical listeners or viewers to try and write down a proposition in which is independent, unconditional of any other conditions whatsoever. No statements, no nothing. You will find it is an impossible task. There will always be some conditions. All probability, like all logic, is conditional on something. And so that's our first mistake on this right here. So we need to fix that. And there is this, it's a smaller error here. It's a smaller error here, but we need to understand this. He says, knowing that F has occurred generally changes the chances of E's occurrence. Well, he has a slight bias towards an empiricism here, which is to say he's thinking of propositions E that are entirely empirical. That is to say, they exist in the real world. It's a measurement of a physical thing, like a dice throw will do, or coin flip, or blood pressure, or anything you can think of. But it doesn't have to be that way, of course. The E and F could be absolutely anything we like. The heater kicked on and it's too hot, so I had to shut that off. And his conclusion is this. The conclusion is the probability of E and F, which of course we're using, as always, the Boolean notation. The probability of E is true and the logical and F is true is equal to the probability of E, probability of F. That's the error he makes. I say this means F is irrelevant to E and E is irrelevant to F since the order doesn't matter here. But they both need some conditions. They all need some conditions, whatever they're going to be, some set of conditions, X, some proposition, whatever that's going to be. And that can be true, but we can't have it without the X's. That's an impossibility. And however easy it is to write a notation, I've emphasized this point over and over again, you will find yourself running into error if you don't make this distinction. And again, I've given examples like before. We could have one of our statements is we must pick. I think I used last time Bigfoot and a happy feminist or something, and a alien from a UFO or in a room, and only one is going to walk out. What's the probability that Bigfoot walks out? Well, given that evidence, the probability is 1/3. Even though, of course, none of these things exist, but we can still calculate probabilities based on them, just as we can calculate or analyze logically the relationship between things. And never forget, this is why I love this notation here with the bar and everything. I'm not the one who invented this. It came long ago, but what it's very nice about this is it emphasizes probability, like logic, is the relationship between propositions. It doesn't tell us where the propositions come from or how they originate or anything of that nature. It just says, given this bunch of stuff on this side, which we're going to assume is true, what is the relationship between these propositions, which I've made up and I stuck on this side? What is the relation? This right here is the relationship. So what is the relationship of these to these? And now that's a very nice notation because that's all probability is. Probability is not physical. Probability doesn't inhere in things. Nothing has a probability like it has a measure of something else, and I'll prove it to you. Yet again, I'm going to give you an example here. I think a better example, I'm going to continue with this E and F notation that Ross uses. And I'm going to give us, to show you why we have to have that conditioning information and why I like the term irrelevance better. First of all, because we're not, well, let me just give you the example here. So let's give these two here. So I'm going to have this proposition E here. I want to make sure I use the same thing. Okay, score on some game is going to be greater or equal to 4. We have some game and we're keeping score, and the score is going to be greater or equal to 4. Okay. Now, here's our F. Device 1 shows a 2. Alrighty, that's it. That's our information. We have the score of on this game, whatever this is going to be greater or equal to 4. And we have device 1, maybe I'll just notate it like that a little bit easier. Device 1 shows a 2. So what's the probability of E given F? Doesn't have one. At best, there's no probability we can really infer from this except for F and the knowledge we have about, I told us from day one, you know, and I reminded us again when we started, the definitions of the words, the symbols, and all that kind of stuff are all part of this. So we can infer that E is contingent. The universe does not have to be such that the score is necessarily greater or equal to 4 or less than 4 or any other number. So this, we might say, equals the entire unit interval, just to emphasize that E is contingent, which is adding, and it's not strictly, I did this last time too, it's not strictly 0 or 1 because we can't infer that E is certainly true or certainly false given F. There is no, what's the probability of E? There is no probability of E. It doesn't make any sense. The score is greater than 4. The score is greater. What score? What are we talking about? Score. Again, there's no conditioning information. Likewise, we have no probability of F. The device 1 shows a 2. Does that mean there's a device 2 or 3 or 4 or 5? We have no information. So there is no probability of E. There is no probability of F. There is no probability of E given F. Okay? So let's try something else here. We need some additional information. And one set of information I might have is, I call it X here. There's a game adding, okay, I'll spell out adding device 1 plus device 2. This is how we're going to score the game. And each device can shows the numbers 1, 2, 3, 4, 5, or 6. Aha! Now we have some information. So now we can calculate certain probabilities. Now we're in town. We have something that ties E to F. We have some additional information that we can calculate. Now we can calculate the probability of E given of X. We can calculate this. We can add 2 devices and each shows 1, 2, 3, 4, 5, or 6, and we want to score greater than 4. Well, that's easily seen to be 36. 33 over 36 possibilities. I mean, I'm not going to go spell them all out. These are similar to dice. The only possibilities is we get a 1 on device 1 and a 1 on device 2, or we have other. Should that be 32 over 33? 6? Whatever. The only we get a 1 on device 1 and a 2 on device 3. A device I can't speak English. We get a 1 on device 1, a 2 on device 2. That's a score of 3. On device 1 we get a 2, and on device 2 we get a 3. That's a score, a 2, we get a score of 3, or we have a 1 on both of them, that's a score of 2. Any other number gives us, any other combination of sums we get are going to be 4 or greater, so we only have 33 over 36. Okay, we can calculate that. That follows from the statistical syllogism, as we learned, and so forth. These don't have to be real things. They could be the states of metalunan interocitors. They don't have to be dice. They don't have to be real at all, but we can use this model of dice if we want to call these things dice. All right, so we can calculate now the probability of F. We can calculate that easy enough. The probability of F, the device 1 shows a 2. Well, that's now 1/6. Again, using the statistical syllogism, no problems there. All right, now we can calculate 2 other probabilities. We can calculate the probability of E given X times the probability of F given X. Well, that's 1/6 times 33 over 36, and that equals, I did it here, as 153. Or we can calculate the probability of the two together, we can calculate the probability of here, probability of fx. This states, and this is approximately 139. This states this is the probability of E and F together. This is the probability of f of x, which is still 1/6. This is the probability of E given we know f is true, or we assume f is true. Given that we assume the second device shows a 2, what's the probability the score will be greater than or equal to 4? And we could calculate that out with absolute ease, which is this particular probability happens to be 5/6, and this will be 1/6. Okay, so it turns out that knowledge of f is relevant to the knowledge of the score of E, given x. So again, assuming we know x, knowledge of f is relevant to knowing the score, because these two probabilities here are not equal. These two probabilities are not equal, therefore f is relevant to knowledge of E. But they're not in any way dependent on one another in any physical sense. This is why I don't like the word. It's not a wrong word, it's just not very useful, because if you think of f as dependent, device one, if you are rolling, here's some devices right here, and if I'm going to roll one and then roll the other, one over here and one over here, in no way are they causally related to one another. And so the score on this one is not going to have any influence of the score on this one. So one is not dependent on the other. But knowing the score on one tells me something about the total score of the game. All right, so the two events, dice throws, are not dependent on each other in that way, in a causal way, in any kind of physical way or anything like this. But they tell us information. And just to give you an example, to complete this example, I'm going to erase this part. I'm assuming you have it here. Just to save space. And to show you, again, why it makes it, remember, it's the probability of f and x. E given f and x. So it's given f and x in the face of f and x. We can't just have the probability of E given f. That doesn't tell us anything. So I can have a different condition. I'm going to get the exact one that I have in the book here. Okay. The score is device 2 only, but there are two devices, still D1 and D2. And 1 through 6. There are still D2 and D1. There are still two devices, but the score is device 2 alone. That could be a game. Now the probability of all these things, the probability of E given W. The score is greater than or equal to 4. Why, that's now greater than or equal to 4. That's only 4, 5, 6. So that's half, right? The probability of F given W, device 1 shows a 2, that's 1/6, right? The probability of, okay, the probability of E given F W is now, well, this is F. F says the probability of device 1 shows a 2, but the score is only going to be D2 only. So knowledge of F in relation to W, accepting also W is true, tells us nothing about E. So knowledge of F here is, again, irrelevant. It was relevant when we had different information about how to treat the score. So the probability of E and F by themselves don't exist, don't give us anything. This is it. This is simply it. Nothing more than this. So we need this extra conditioning information that tells us how to tie everything together. And so in this case, we can see that F is absolutely irrelevant because these two probabilities are the same. knowledge of what happens on the first device doesn't tell us anything about the second device. There's no causal relation to one another. There's absolutely nothing to do about cause, and yet we could still calculate probabilities. The classic example, and we've heard this, if you've taken probability of stats classes before, maybe you've heard this in other contexts. They say, I don't know if it's even true, but you've heard it said that ice cream sales increase. As ice cream sales increase, so do the number of drownings. And so here's number of drownings, and here's number ice cream sales, and there's some relationship like this, loose relationship like this. Well, it seems that ice cream sales are relevant to knowledge of whether or not someone's drowning. Well, the teaser to all this is what they tease you is, of course, ice cream sales go up in summertime, and people swim in the summertime, and they don't swim so much in the wintertime, at least not up here in northern Michigan. So there's not going to be very many drownings. So there's no causal relationship between the two. Ice cream is not causing the drownings, but it's still a good model. All right? The probability of drowning, oh my goodness, I keep dropping the chalk. The probability of drowning given ice cream sales that are a certain level, ice cream sales level, that's still useful information. We can have that model. We can absolutely use that model to make predictions, but it's not a causal model. It's a correlational model. And as long as we keep that in mind, we can absolutely do this. But the interesting thing is they'll teach you this kind of thing to teach you that the probabilities are not really the same and all this kind of, the way they do conditional, unconditional probabilities. And then with a straight face later, they'll teach you something called hypothesis testing, where you're not allowed to bring in this external causal knowledge, or there's no coherent way to do it. Or people don't use hypothesis testing all the time when they have causal knowledge. We're going to get into all that hypothesis testing stuff. There's absolutely no way to be consistent while using it, and it's always a logical fallacy when you do. Instead, we could recognize things like this. We could recognize there's some causal factor in here that we don't understand how to exactly track, but we have all these numbers, we have these numbers, and we can form some sort of a useful model as long as we're acknowledging that this is just purely correlational, and there's no dependence in a physical way on these things, not in the causal sense and so forth. Now, there's more to this, but I think I'm going to quit there because it's just gets more. I mean, I talked about it last time a little bit. It's in the examples we had here. It's the probability of E given F and X, and the X was how we scored the game. If we can't derive the F from the X or the W and relevance and all that kind of stuff, there's more technical ways you could look into all this, and it has all sorts of uses when you're really calculating probability. And the first person to make this distinction, as far as I know, is Jaynes. The same Jaynes, the economist Jaynes. He wrote a book called A Treatise on Probability. It's now about a century old. And it's a fantastic book. It's you can get it. Dover has reprinted editions of it and so forth. He treats probability in a logical sense, as we do, as Jaynes does, as Stove does, as all these other people do. And there's all sorts of rich ideas and so forth. And as far as I know, he was the first to make this distinction between relevance and dependence. Because probability is logic, we can exclude this idea of dependence and so forth. Because don't forget, nothing has a probability. There is no probability of E. This thing doesn't exist. And so if it doesn't have a probability, it doesn't have a probability distribution, which is when E can take several different possible. This is like a generic proposition where E can take E1, E2, E3, E4, E5, something like this. And so the idea you'll see all this time, and we're going to run into this, is independent, identically distributed E. And then they'll say, well, you can't use... First of all, this doesn't exist. Nothing has a probability, so nothing has a distribution. Our uncertainty with relation to some evidence might change how we think about E. Absolutely true. And that's fine. And so some people will say, well, you can't model, well, we'll get to it when I give you more particular examples and so forth, but they'll say, oh, you can't model this because you're not taking into account the dependence between certain variables and so forth. That's absolutely not true. You can use any model you like, using whatever information you like. You don't because when people say things like that, they're thinking that certain causal relationships exist between certain variables. Of course, if that's true, you should be using causal relationship between variables and so forth in your models, but you don't have to. I mean, a model is just like a probability, and you could put anything you like down, any two propositions or multiple propositions on either side of this equation, and calculate the relation between them. Things don't have probabilities. Things don't have correlations. Things don't have distributions and so forth. And so all this terminology is wrong. It just leads you to, and also Ross was going on about, in order to, he also says, in other places he says on page 9, he says, an infinite sequence of independent trials is to be performed in order before we know any probability. Remember that back when we did why we showed that frequentist probability is not a thing. No frequentist is ever coherent either. They never think like a true... The theory demands one thing. They stick to it only at times and then abandon the rest of the theory when it's convenient. So every frequentist theory has to be of real objects because you can't have... the objects have to be in repeated trials, and no probability can ever be known until the repeated trials goes out to infinity. And it's from kinds we get, and so in the long run, they say, as a euphemism for getting out to infinity. And it was Keynes himself who said in this relationship, in this context right here, in the long run, you know, we shall all be dead. So frequentist probability just doesn't work. It doesn't function. It's not a real thing. And we went over that a long time ago. I can't even remember, like, you know, lesson 10 or 12 or something like this. You can go back and look at the series and find out. All right, I'm kind of rambling today. Language matters, right? The words we use make a difference, and they condition our mind to think one way or the other. And so I want us to use a coherent, meaningful language that won't lead us astray when we think about probability and when we think about models. And so we don't get led into the deadly sin of reification, which is assuming our models, IID, and that kind of stuff are real. All right, probability is a matter of the mind. It does not inhere in things. And so if we use language and we're not careful about it, we can lead ourselves astray into that world. We're going to see this error happening again and again and again, I promise you. All right, so next time I think I'm going to show you maybe a little something on Bayes' theorem. Bayes' theorem is, of course, wonderful and all that kind of thing, but it's not the most important thing by far. There's this false dichotomy out there that there's only frequentists and Bayesians in modeling, and that's just not true. It's absolutely not true. We're neither frequentist nor Bayesian. I'm a logical probabilist. I am just plain probability, that's all. I think that's the best way to sum up our belief in probability. And then we're going to talk about parameters. Maybe we'll do both or something like this. The mathematization of these probability distributions and so forth, which will turn out to have a lot of benefits and a lot of ways for new errors to creep in. All right, that's it for now. More down below, wmbriggs.com or wmbriggs.substack.com. Thanks very much for listening.